Tim Kim wanted me to ask the room, who here is a JavaScripter? Raise your hand. And who's a JavaScripter? Okay, right on. There you go, Tim. Okay, so this is FTL, Faster Than Light Adventure, and we're going to just jump right into it. I work on a project called Surge. My name is Brock Whitten, and Surge is a front-end publishing tool for front-end developers. It's fun to use. Give it a go. And this is supposed to work. Here we go. Who here's seen this video? A few people. Okay. So I think this is called fading light, and what this is we're traveling at the speed of light from the sun. And we're going to go through the solar system together. This is the speed of light. All right? Kind of slow. All right. 22 minutes to Mercury. That's kind of crazy. Oh, geez, this is 6 minutes to Venus, 8.3 to Earth, 12 to Mars, 46 to Jupiter, 79 to Saturn, 159 to Uranus, 4 hours to Neptune, and Pluto, well, no one cares about Pluto. The speed of light is really not that fast. But yet, it's the fastest thing that we know of, or that I know of. And what can we do about this? Because we're very much bound by it. Maybe there's some insight here. So Albert Einstein said, the power of compound interest is the most powerful force in the universe. Okay, well, speed of light's the fastest thing in the universe. Maybe we can use the most powerful force in the universe to, try to conquer it somehow. But like, Albert Einstein isn't passive-aggressively tweeting about losing a couple grand on the stock market. He's not a day trader or anything like that. So why is he commenting on compound interest or whatnot? Well, Albert Einstein likes to see things and observe things that maybe aren't intuitive. And he did this a lot. And he's basically just analyzing natural phenomena, or the way that the world is governed and the universe is governed, and that's what he's commenting on. And this isn't terribly intuitive, but it impacts us in every single way that we can think of. And I'll just use another example. So say that we have this piece of paper, right? And it's like 1 millimeter thick. And if I fold it in half, it's now 2 millimeters thick. I'll fold it in half one more time. And now it's 4 millimeters thick, okay? So I've like folded this a few times, and actually it would be 8, I don't know. It doubles every time. But it's compounding, and we can keep folding this, and of course, like, there's physical constraints here, but let's pretend for a second that I can fold this paper infinitely, right? And let's see how high we can get this stack of paper. So how many folds is it going to take for us to like reach the ceiling in this roof, or like the roof of this building? Does anyone want to venture a guess? 20? 100? Okay. If I fold it 41 times, I'll give you a hint. If I fold it 41 times, it will get us halfway to the moon. For real. If I fold it, which means if we fold it 42 times, we're at the moon. That's not very intuitive, is it? So why isn't it intuitive? Especially once it's been explained to you, it still is like hard to grasp. And there's like a parable, famous parable on my slide. There's a couple back, there it is. Where this farmer is meeting a king, and the king wants to reward him, and he asks him what he would like. And the farmer's like, well, how about this? You put 1 grain of rice on your chessboard at one piece, And then every subsequent square, I want you to double how many grains of rice are on there. And of course, the king was like, yeah, that sounds like more than reasonable. That's like a very humble request. Well, really, this request is like, it's more rice than has ever been made on planet Earth, ever. And of course, this request would be absurd, but this wasn't intuitive to the king. And so he granted it to this farmer, and he looked like a fool for it. That might have happened, it might not have, but anyway. So why isn't it intuitive? There's certain things, the way that we think, that are kind of broken. And the analogy that I would like to use is like optical illusion. So you get shown an optical illusion, you've seen this 100 times in your life, and it's like, oh, these lines are all crooked. And you're like, yeah, of course, they're crooked. But then someone points out, like, no, if we actually measure it, all these lines are completely parallel. And you could get a piece of paper and get out a ruler, and you can look at it, and you're like, yeah, wow, that's really surprising. I didn't know that. Thanks for pointing that out. And then you unfold the paper again, and you step back, and you're like, well, those lines are crooked, right? And like, our brains are broken, and we make decisions every day, and we make poor decisions every day based off of these unintuitive behaviors that we have. We think very linearly. We think that if we put in twice the amount of work, we get twice the amount of benefit. And I'm not exactly sure when this changed. Maybe it was like when we started agriculture and we got the concept of planting seeds in the ground and it multiplies and things like that. But it's something that it's a principle that we've had to drill into ourselves. And it's always surprising. So let me give you some context about where I want to take this. I'll tell you a little bit about how Surge works. It's a static hosting platform. And it doesn't work like how you would typically expect. There's basically one directory that's just full of files, and these files don't have any extension or anything. The file name is based off of the contents, the 256 sum of the contents, and any file, no matter who publishes it, it goes into this directory that can be stored anywhere. So we have some long-term cold storage, and we've got edge nodes that can pull down from it, etc. Then we've got another directory that is a list of projects, right? These are just JSON payloads that look something like this. This is almost exactly verbatim. I had to shorten those 256 sums a little bit. But this tells us how to serve this file. This tells us it's an index.html file. That SHA is where to get it. We use the MD5 for just some other niceties for e-tag and stuff. And the size, so we can put proper headers and everything in our request. So basically, we end up doing a lot of this where a request comes into an edge node. It's usually like this is the stack that we go with, and this middle layer is just a proxy to whatever truth is, right? And truth could be anything, and it could really be anywhere. And I'll show you why. So naturally, we need to reach over to the network at times if we can't find the file that we're looking for. And that might look something like this. Nox is an S3 library, and we would just say, hey, someone's visiting Cascadia.js. Let's go get this manifest file that's going to tell us all the files, and then let's serve the appropriate file from our big, giant directory full of files. Okay. Let's presume that the best this can do is like 1 request per second. Not terribly fast. We all know that Node can proxy a lot better than that, especially with non-blocking, but for the sake of argument, we'll just go with this. Naturally, it would make sense to utilize the disk. Like, well, let's take this JSON payload that could be on S3, and after it's been requested, let's just stick it into this directory, and then we can access it later. So the next time someone goes to visit Cascadia.js or request another file, we just fetch that from the disk, and we serve it up. And if it doesn't exist, then we go and get it from the network. Well, purging these files is pretty easy. Unix makes this a breeze, so We can do things like we can delete all the files that haven't been accessed in 90 days, or all the ones that are greater than 1 meg and haven't been accessed in 21 days. You can just purge, and the purpose of this is not for cache expiry so much as just making sure we don't run out of disk space, right? So this could be like a conservative estimate. This is the principle that I want to tell you about, which is that we can now get like 1,000 requests to our local disk in the time that it would take to do a network request. So we can get like 1,000 disk requests per one network request. This is pretty sweet, right? Well, we can do a lot better than this, and I think most of us know that, especially when we start introducing things like Redis. So let's do that. Let's put this in Redis. So before we go to disk, let's go check Redis first. And this is maybe the wrong slide. But anyway, this is how you would set it in Redis. Oh, that'd be correct. And then next time we go to access it, we'd read it from Redis. So there's this other principle, and I talked about this in the first Cascadia in Seattle, that the time it takes to access these different parts of your stack is like orders of magnitude. So I use this analogy of like, oh, like RAM going into Redis is like flipping open a notebook and just like looking it up. But obviously you can't store a lot of data there. Going to disk would be like getting in a car and going into Blaine to the library and getting out a book. Accessing the network would be like going to Seattle International Airport, flying to New York, going to the library there, flying back, and then serving that request. So these things are very expensive. So there's a lot of win by accessing, these more immediate, faster parts of the stack, like orders of magnitude. So now we've got 1,000 requests in Redis for every one that hits the disk, and we got 1,000 disk requests for every one that hits the network. Like, you must be thinking like, surely we can't do any better than this. And I would say, we can, and don't call me Shirley. So it turns out, like, JSON.parse is pretty expensive. It's got, it takes CPU to do this. And this is now our bottleneck. So now we're using Redis. There's really nothing faster than Redis, right? But we're bottlenecked again because we got to keep parsing these payloads all the time. Well, we can actually go one step closer to the user, and we can put this in like an LRU cache right in the process. And of course, this is even smaller. So this is like writing a note on your hand, scribbling a little note. And so when a user comes in to request a site, like usually they're gonna like request a bunch of pages, right? So it makes sense to have a cache that's really hot, that's ready to go. And this is a huge win. It's like another orders of magnitude over Redis. And so that would look something like this, where we'd get it before going to Redis, and then we'd check Redis before going to the disk, et cetera, et cetera. Okay, well, now we're getting some of these compound benefits. We're starting to see like the rice situation on the chessboard, right? So we're getting 1,000, we can serve up, and I'm making up these terms, obviously, but we get roughly like 1,000 requests that we can serve right from the process before hitting Redis and parsing the payload. We can get 1,000 Redis requests before hitting the disk. We can get 1,000 disk requests before going to the network. We just basically increase the capacity of this machine to like by a factor of 1 billion, for real. And this is just like those same principles applying, these principles that Einstein was talking about. So I know what you're probably thinking. You're probably thinking like, yeah, of course, like this isn't something that like really practically can scale forever. And it probably isn't, but what it does do, and this is what the beauty of Node.js is to me, is that it makes it really easy to push the bottleneck elsewhere. And by elsewhere, I mean like you're pushing it to the OS or you're pushing it to the network. So now it's like, how fat is your network? How much disk space do you have? How much RAM do you have? You're really like, you're now hardware bound or you're OS bound. It might be file descriptors, but it's really nice that you can do this because you can now focus on other areas of your stack. And when you do this, you start to see a node process like you used to see a machine, and you start to see machines like you used to see racks or data centers. And it's very empowering. So there is another win that I'd like to tell you about, which is kind of interesting. So it's this project called inflight, and I think it's used in NPM. And this project's got like, I don't know, maybe 30 stars on GitHub. And I really like this about NPM is that there's like some real gems out there that like are hardly used or known about at all, but they're really amazing libraries. And what this does is, I like to call it like the when to get milk kind of paradigm. So let's say you come home from work and you go into the fridge for a nice cold glass of milk. And you realize that, oh, you're out of milk, what a bummer. And of course, you're like, well, maybe I'll go and get some. So you're about to go get some milk, and your roommate had already left you a note, like, gone to get milk. It's like, oh, sweet, well, now I can just sit and watch the baseball game or whatever until this milk comes back, and then we can both drink it together. And you're having a bit of a milk party watching baseball. So what this library does is it writes that note. So when someone goes to do a request for, it could be a database query or it could be fetching a file over the network, but it says, hey, I'm gonna go get this payload. I'm gonna go get this this request, and then when I come back, like anyone else who wants it can use it. So that's pretty useful, and in particular, the reason why that's useful is because we end up with this situation where like a website might be getting a lot of traffic, and then they publish a new version of their site. And of course that like updates, the lowest part of the stack, the truth, and then it blows away the cache, all those caches, so that the next request that comes in, it gets refreshed all the way down. And the problem with that is if there is a lot of requests coming in, and that website might have a bunch of like script tags and everything that like even one user, it needs to make like 20 requests to that domain. And so all these requests come in all at once because the cache is cold, and they all need the same thing, and they all miss the caches all the way down the stack, and then they all are going over to S3. So they're all hitting the network. And that we can't necessarily make that faster, but that's very resource intensive, and if you rely heavily on caches, one of the downfalls that you can run into is that when you have a cold machine and the caches aren't warm, that you just get like obliterated when you spin up these machines. And I think like Twitter ran into that a lot back in the day. This is like quite a while ago, but when the whole fail whale thing was an issue. I think that like they ran into those issues where they're just like, oh, the caches are cold, like baby this thing until it's warm again. So this problem's real, and this library can help. So I know you're thinking like maybe like, oh, this is great and all, but like, okay, we're kind of out of orders of magnitude. There's no more orders of magnitude left. We've cached the network, we've cached on disk, we're using RAM, we're even using processes and caching in there. Like, there's nothing left. But that isn't true, because there's another layer, and these tiers exist all over the stack. And the browser has these as well. So the DOM is like the disk, and it's expensive, and you shouldn't touch it if you can help it. And this is what libraries like React do so well, is that it's just caching in process. It's like the LRU cache. It's just like a slightly different paradigm, but that's what it's doing. It's just preventing you from hitting disk more than you need to, and in this case, the DOM. There's also this other wonderful thing that's on the horizon, or here, depending on who you talk to, which is service workers. And what this gives us is this gives us another layer closer to the user. So this is like a really big deal because we've basically done all we can at this one layer. So we've really optimized that step once it gets into our process. And it doesn't even really matter how far away truth is. That could be a server on the moon, really. And it's fairly optimized. But what about that other red arrow that's causing us grief? And this one, we all know this really is causing us grief. And the service workers is giving us another order of magnitude by giving us a layer closer to the browser or at the browser where we can prevent unnecessary requests going to the network. This is really awesome. This talk isn't about service workers, but anyway, that's basically what I wanted to show you guys in terms of beating latency and getting way more out of your hardware. And start thinking about those layers, and you certainly don't have to utilize them all, but what I most want you to get out of this is just the principle of compounding and how it's not just a financial term, it's not just something that happens to your credit card bill. But on that note, it is something that affects you both positive and negatively. So you want to be definitely in front of the wave and not behind it if you can be. I was going to just talk about the DMCA a little bit. Well, actually, I'm not going to talk about DMCA. I'm going to talk about how we need to start talking about these things more as technologists, because it's certainly affected me a lot. Is there people here who DMCA has been affected or has affected them or their business? Okay, not a lot. Okay, but we should talk for those who have been affected or don't know how to deal with this. It's caused me a lot of grief recently, and it's hubris of us to expect that policymakers are going to come to us. They're going to get more enlightened in technology and how to bounce the scales better, right? So I think it's on us to come to them to try to understand these laws better, what's appropriate, what isn't, what's legal, what's fair to the users, what's fair to the copyright holders, and so I just want to encourage everyone to just try to understand this stuff more and talk about it and try to do something about it if you can. So I'll leave you guys with this. This is kind of an interesting quote. Warren Buffett, famous investor. It's kind of going full circle back. But he just says, someone's sitting in the shade today because someone planted a tree a long time ago. This compounding is something that affects every aspect of our life. And I just want to encourage everyone here to think in those terms. Think about the investments that you're making, the companies you're working for, the companies you support, the friendships that you make, the libraries you contribute to. You're building something that that others will be able to compound on top of. So plant a tree, whatever that means to you, and yeah, if you can, try out Surge. It's easy to use, and thank you very much.
All right, thank you so much, Brock.